talk about oscillation. First, we'll define what simple harmonic oscillation is. Then we'll analyze position, velocity, and acceleration for a simple harmonic oscillator, and derive the frequency for a mass on a spring using an energy approach. We'll finish by solving and analyzing a sample problem. A simple harmonic oscillator is an object that exhibits motion that can be described by a sine function. We can call it a sine function or a cosine function since they're the same thing, modulo initial angle. For this simple harmonic oscillator, we can define the position function as a function of time as the amplitude times cosine omega t plus phi 0. The amplitude is given as 2 pi times the frequency, or 2 pi divided by the period t. We can find the velocity function for a simple harmonic oscillator by taking the time derivative of the position as a function of time. Taking the time derivative of a cosine omega t plus phi 0 gives us minus omega a sine omega t plus phi 0. We can find the acceleration by taking the time derivative of the velocity function, giving us the acceleration as a function of time is minus omega squared a cosine omega t plus phi 0. We can also use these functions to define the maxima of the velocity and acceleration for a simple harmonic oscillator. For the maximum velocity, we just recognize that minus sine omega t plus phi 0 has a maximum value of 1, so V max equals omega a. Similarly, we find the acceleration maximum to be omega squared times the amplitude. Notice where the position function equals 0, the velocity has a maximum or a minimum. That makes sense. When the mass is at equilibrium, it's moving the fastest. Where the position function is a maximum or a minimum, the velocity equals 0. That's where the mass is turning around. Now let's look at the energy of a simple harmonic oscillator. In this case, we'll look at a block of mass m attached to a spring of constant k. We'll consider that it's on a frictionless surface. The total energy is the kinetic energy plus potential energy. Since we're not changing the height of this system, there's no change in gravitational potential energy. So the total energy is just 1/2 mv squared, which is the kinetic energy, plus 1/2 kx squared, which is the spring potential energy. At some point in its oscillation, the total energy could be either all kinetic or all potential energy. When the velocity is the fastest, when it's moving through equilibrium, the total energy is 1/2 mv max squared. When the mass is at its turnaround points, then x equals the amplitude value, and the total energy equals 1/2 k times the amplitude squared. We also know that the maximum velocity is omega a. If we substitute that in for V max, we get 1/2 m omega squared a squared equals 1/2 k a squared. We can cancel the 1/2 factor and the a squareds and solve for omega. This gives us the frequency of this simple harmonic oscillator as the square root of k over m. Let's use this to solve a simple problem. Here we have a block of mass m attached to a spring of constant k. It's oscillating horizontally on a frictionless surface. The block is moving at speed v1 when it's a distance x1 to the right of equilibrium. The question is, what is the amplitude of oscillation? We start with a diagram of our system. We've identified the equilibrium position and that the block has a position and velocity. We'll start with our general equations, specify our equations for the system, solve symbolically in terms of given variables, and analyze results. For this problem, we know the mass, we know the spring constant, we know the position and velocity at one position, and we want the amplitude. Our general equation is the energy equation we just looked at, so 1/2 mv squared plus 1/2 kx squared, and we can let it equal 1/2 mv max squared or 1/2 k amplitude squared. That's our general equation. For this system, when our velocity is at v1 and our position is at x1, we can equate that total energy, 1/2 mv1 squared plus 1/2 kx1 squared, to the energy that the system has when the block is at its extreme point, 1/2 ka squared, where x equals the amplitude. We can solve this for the amplitude A, giving us square root m over k times v1 squared plus x1 squared equals the amplitude. We can do a little bit of analysis here. The bigger the pair, ordered pair x1 and v1 are, the larger the amplitude. That makes sense, since it would be moved farther away from equilibrium and moving faster. That means that the total amplitude must be bigger. Also, the larger the mass, the larger the amplitude. That makes sense too, because a larger mass means it would, for the amount of energy given, it would have to have a larger amplitude to keep the other quantities constant. The larger spring constant would give it a smaller amplitude. That makes sense too, since a stiffer spring would not tend to move as far given everything else was the same. To recap, we saw that a simple harmonic oscillator is a system that has a motion that can be described using a sine wave. The total energy is the sum of kinetic and potential energies. For this system, we used the spring potential energy of 1/2 kx squared. We also defined the frequency in terms of the mass of the oscillator and the spring constant k, as omega equals square root k over m. Thank you very much for coming. Please come back again soon.